Now we're going to talk about equilibrium between phases. And when we say phases, we are referring to, for example, solid phase, liquid phase, gas phase, or we're referring to different types of phases even in solids like crystalline phases, etc. So a good example is the transformation between these phases for the case of gas, liquid, and solid phases. For example, if the solid phase is transforming into the liquid phase, we have the so-called process of melting. If the liquid is transforming into gas phase, we have the process called vaporization. If, on the other hand, the gas phase is transforming into liquid, we have condensation. The liquid phase forming a solid phase, liquid to solid transformation, is called freezing. And similarly, we can have a direct transformation from a solid to a gas, that's called sublimation. So all of these phases um, will occur in a certain range of temperatures and pressures. So we have to find the correct range of values for temperatures and pressures that will stabilize the phase formation. Now you can think of a scenario where I have a possible coexistence between two phases, and as you can see that phase 1 and phase 2 in the system coexist, and when they are in thermal contact and the contact is through a movable piston with a reservoir at constant temperature T and pressure P. So this is basically the scenario we have studied in the previous video, where we talked about the minimization of Gibbs free energy. So let's, for example, think of phase 1. This could be water phase, liquid phase. Phase 2, for example, could be ice, that is a solid phase. So for these two phases that coexist, we have, since we have a thermal contact between them, temperature of phase 1 must be equal to temperature of phase 2, must be equal to temperature of the reservoir T. The pressure in phase 1 must be equal to pressure in phase 2, and that must be equal to the pressure of the reservoir. And if I look at Ni is the number of molecules in phase I. Then I have the number of molecules in phase 1 plus the number of molecules in phase 2 equaling to the total number of molecules, N. So capital N is total number of molecules, and that must be a constant. Obviously I cannot have the matter disappear, so there's going to be conservation of matter in the phase transformation process. I will have the total number of molecules conserved. And the question I would like to answer is basically, at the temperature and pressure provided by the heat reservoir, at temperature T and pressure P, do these phases coexist or not. So the possible scenarios would be I have only phase 1, I have only phase 2, or I have a mixture of phase 1 and phase 2. Now, in order to answer this question, since we have a system in contact with a constant pressure and temperature reservoir, we need to look at the total Gibbs free energy. The total Gibbs free energy by definition is the mean energy E bar minus Ts, absolute temperature times entropy, plus pressure times volume. So this is the total Gibbs free energy of the system. And it consists of two components. There is the Gibbs free energy of phase 1, and there is the Gibbs free energy of phase 2. So if you look at the mean energy of the system E bar, that will be the mean energy of phase 1 plus the mean energy of phase 2. That will give me the total energy. If I look at the total entropy, S will be entropy of phase 1 plus entropy of phase 2. If I look at the total volume, it is V1 plus V2. So you can see that the total Gibbs free energy, G, will be the sum of the Gibbs free energies of the first phase and the second phase. So you would have E1 plus E2 bar equaling to E bar, minus T parentheses S1 plus S2 equaling S, and plus P parentheses V1 plus V2 equaling V. So the total Gibbs free energy is the sum of Gibbs free energy of the first phase plus the second phase. And this is because the mean energy E bar, the entropy S, and volume are extensive parameters. So they depend on the size of the system, and therefore we have the total Gibbs free energy or Gibbs free energy per phase is an extensive parameter as well. So in order to make it intensive, so one can write the Gibbs free energy of phase 1 as the number of molecules in phase 1 multiplied by Gibbs free energy per molecule. And similarly, we can write for Gibbs free energy of phase 2, number of molecules in phase 2 multiplied by Gibbs free energy per molecule in phase 2. So we define here Gibbs free energy of the ith phase per molecule. Gi as a function of temperature and pressure is the Gibbs free energy per molecule of phase I at the given temperature T and pressure P. And you can see that the Gibbs free energy per molecule for the ith phase is not a function of the number of molecules in that phase. So this is basically intensive. It's becoming an intensive thermodynamic parameter. Therefore, we can write for the total Gibbs free energy N1G1 plus N2G2. Now, under what conditions will these phases coexist? Well, we would like to require that at equilibrium, the total Gibbs free energy must be minimum for both phases to exist. So both phases, this is the condition for the coexistence. Both phases coexist, then the total Gibbs free energy must be a minimum. And remember that the total Gibbs free energy becoming a minimum basically guarantees that the entropy of the system is maximized. So going back to our previous discussion, you can see that S star is maximum. The total entropy being maximum is guaranteed by the total Gibbs free energy becoming minimum. So that's the same condition. So how can I guarantee that the Gibbs free energy is a minimum? So we need to look at the extremum of the Gibbs free energy. If I write dg, infinitesimal changes in the Gibbs free energy, it will be by changing a number of molecules from one phase to another phase. So this will be equal to Gibbs free energy per molecule in phase 1 dn1 plus the Gibbs free energy of per molecule in phase 2 dn2. This must be equal to 0 at this extremum point. And because I have n1 plus n2 equals to n, a constant, dn1 plus dn2 equals to 0. So dn1 is equal to minus dn2. Basically, the number of molecules that transform from phase 1 to phase 2 is the same, or phase 2 to phase 1 is the same. So we have the new number of molecules in phase 1. dn1 is minus the number of molecules we have lost in phase 2. So it's minus dn2. So this is going to give for us G1 times dn1 plus G2 times dn2 is equal to G1 dn1 minus G2 dn1. And this must be equal to 0 for extremum. So this is dg for the extremum point of the Gibbs free energy. So this will basically imply that G1 minus G2 dn1 is 0. So therefore we find that for coexistence in equilibrium, the Gibbs free energy per molecule in the two phases must be the same. So it's a direct consequence of the minimization of total Gibbs free energy. For coexistence in equilibrium, we must have Gibbs free energy per molecule the same. So basically, if you have a number of molecules transforming from phase 1 to phase 2, if there is a dn1 which is non-zero, it doesn't affect the value of the Gibbs free energy, total Gibbs free energy, G. All right, so that's the meaning. So the transfer of one molecule from one phase to another does not change the total G because it is at an extremum point. So there is no preference for the molecules to go through a phase transformation. Now you can see that here is a plot of pressure and temperature values And we can see there is a certain range of values where we have the Gibbs free energy per molecule in phase 1 and phase 2 are the same. That is the curve on which we have the coexistence of these two phases. And you can see that if the Gibbs free energy per molecule is less than the Gibbs free energy per molecule in phase 2 for phase 1, all molecules will transform into phase 1. And if we have, so we can write here the total Gibbs free energy G will be equal to N times G1, and here it will be equal to N times G2, and on this curve the total Gibbs free energy will be equal to N1 G1 plus N2 G2. Because G1 and G2 are the same, this will be equal to capital N times G1 plus G2, or 2N G1, because they are the same. G1 and G2 are the same. Okay, so we can basically summarize this result here. If temperature and pressure are such that the Gibbs free energy per molecule in phase 1 is less than the Gibbs free energy per molecule in phase 2, then all N, capital N, molecules will transform into phase 1 so that the total Gibbs free energy, capital N G1, is a minimum. If we have temperature and pressure values such that Gibbs free energy per molecule in phase 2 is less than Gibbs free energy per molecule in phase 1, then we will find that all molecules will transform into phase 2 so that the total Gibbs free energy and G2 is a minimum. And so you can see here for phase 1 capital N G1, for phase 2 capital N G2 are minima, and for the curve of coexistence where G1 and G2 are the same, we have N1 G1 plus N2 G2, so it's going to be equal to G1 in N parentheses, so we will have here in G parentheses, so we have G1 equals G2 equals to G, let's say, so this is G times N1 plus N2, so it is G times capital N. So here it's going to be equal to G1 times capital N, or G2 times capital N. They're the same. So on this curve you have N times G1 equals to N times G2, and that is the Gibbs free energy, total Gibbs free energy on this curve of coexistence. Okay, so we're talking about the possibility of equilibrium between phases. So we have phases like gas, solid, liquid. We can go between phases by a phase transformation process, for example, solid to liquid melting, liquid to gas vaporization, gas to liquid condensation, liquid to solid freezing, or solid to gas sublimation. all these phases can coexist in a certain range of temperatures and pressures. And if you think about the mixture of phases in contact, thermal contact with a reservoir at temperature T, with a movable piston at pressure P, the equilibrium condition is that the total Gibbs free energy of the system must be minimized so that the total entropy is maximized. The total number of molecules N1 plus N2 is capital N, it's a constant. When I say the total entropy is maximized, it's the entropy of the system plus the reservoir, so it's the overall entropy of the isolated system. The total number of molecules must be a constant because there's conservation of matter. If some molecules go from phase 1 to phase 2, we don't have any loss of molecules or any new molecules created in this process. It's the same total number of molecules that is going through this transformation. At what temperature and pressure do these phases coexist? If we write the Gibbs free energy of the system, it's E bar minus Ts plus PV, and it consists of Gibbs free energy of phase 1 and Gibbs free energy of phase 2. Because mean energy, internal energy, is an extensive parameter, entropy and volume are extensive parameters, we can see that the Gibbs free energy is an extensive parameter as well. So it adds up. G1 plus G2 is G. But if we define Gibbs free energy per molecule of a certain phase, it's going to be intensive. So we can write the total Gibbs free energy as N1 G1 plus N2 G2. And for the coexistence of these two phases, the total Gibbs free energy must be a minimum, so that if I look at the infinitesimal changes in the Gibbs free energy, that must be equal to 0 for the choice of values of G1 and G2. And since we have dN1 plus dN2 equaling to 0, dN1 is minus dN2, we see that the coexistence and equilibrium is possible if the Gibbs free energy per molecule for phase 1 and phase 2 are the same. So if you have this condition, the transfer of one molecule from one phase to another phase does not change the G, which is an extremum. So there is no preference of phases for these molecules. If the temperature and pressure are such that the Gibbs free energy per molecule in phase 1 is less than that of phase 2, having all of the molecules in phase 1 guarantees that the Gibbs free energy is minimized. We have G times and G is equal to capital N G1. If G2 is less than G1, then we have all molecules in phase 2, so that the total Gibbs free energy is Ng2. Along the curve of coexistence, it is either Ng1 or Ng2, they are the same. So we find that the total Gibbs free energy is Ng1 or Ng2. So you have a certain number of molecules in phase 1 and certain number of molecules in phase 2. And since G1 and G2 are the same, so it's going to be G1 times N or G2 times N. It's the same thing. So basically this answers the question of how we achieve coexistence of two phases at equilibrium.